Hi everyone, I am Zhen Xie, a postdoctor in University of California, Merced. In this talk, I will present a paper, Tahoe, Tree Structure-Aware High-Performance Inference Engine for Decentralized Ensemble on GPU. This is a joint work with my fellow students and my advisor, Professor Dong Li. Okay, so what's the tree inference? Essentially, is a highly effective structure within which you can lay out options and investigate the possible outcomes of choosing those options. Decentralized inference can be used to help build automated, predictable models. As we can see from this figure, this tree has one root node and multiple decision nodes and a leaf node, which can be used to define whether I accept this job or not. It includes salary, commute hour, and free coffee. These things are helpful for us. How is the decentralized inference actually used? A lot of companies use the GPU for tree inference to average massive thread-level parallelism and high memory bandwidth to provide high-throughput inference. For example, Facebook uses high-throughput tree inference engine on GPU to decide which notification to send to billions of users, as well as Microsoft News selects customized content to display. NVIDIA uses a high-throughput tree library, Rapid FIL, on GPU to serve massive inference requests. So, give a tree ensemble to store. This format it leaves nodes of different trees. In particular, the root nodes of all trees are stored first, followed by left node at the second level of all trees, and followed by right node at the second levels of all trees, and so on. The nodes of each tree are stored in breadth-first order. However, to enable high-throughput inference on GPU has some performance bottlenecks. The first one is different GPU threads traverse different trees and can take different tree passes and access different attributes of input samples during the forest travels, which cause irregular memory access pattern and node imbalance problem. The second one is that give a sample for inference. Each thread uses its assigned trees to make prediction, and then all threads perform a thread reduction to compute the final prediction. It also has high overhead. We study this problem use a random forest trained by XGBoost on a common dataset, Hedges. For the first figure, we observe that the ratio of request data to total data fetched from global memory is only 16.7% because of the uncorrelated memory accesses. From the second figure, the reduction operation takes up to 53% of total inference time in our example with 120 trees. The figure shows the execution time of thread in a thread block. The thread block performs inference for 1,000 samples. We use coefficient of variation to quantify the variance. The CV equals to almost 50%, indicating a large variance in execution time across threads. To solve these performance bottlenecks, this paper proposed Tahoe, a tree structure-aware high-performance inference engine on GPU. Tahoe designed an adaptive forest format to enable coalesced memory accesses and load balance. Besides, we introduced a set of inference structures, each of which uses shared memory differently and has different implications on reduction overhead. We also introduced performance models to guide the selection of inference structures. Then we will introduce them in details. So, adaptive forest format introduces two techniques to rearrange loads and trees. The first one is the probability-based node rearrangement. Based on the information of edge probability, if the left child has lower probability to be visited than the right child, we swap two children nodes. The method goes from top to bottom of the trees. From this figure, the edge probability of two children nodes of the root node at the second level is 0.3 and 0.7. The right child node V23 has higher probability to be visited than the left child node V22. Hence, the two children nodes are swapped. The second one is similarity-based tree rearrangement. We address the node balance problem based on the similarity of trees. We claim two trees are similar if during inference the two trees tend to be traversed using a similar path and accessing similar attributes. As we can see from this figure, the order of the tree lying in memory is T2, T3, and T1. Because of the T2 and T3 have the largest similarity, and T3 and T1 has the second largest similarity. Then, we study how to address the problem of high reduction overhead. We also explore how to make best use of shared memory for high performance. To avoid this reduction and explore performance potential of shared memory, we introduce several inference structures as follows. These structures use shared memory and the reduction mechanism differently. As we can see from this figure, the shared memory usage are highlighted in yellow. We study performance of 4 inference structures using 15 datasets on NVIDIA P100 GPU. The result is shown in this figure. The red marks are the method that corresponds to the best performance. For example, direct method performs better than other structure on 2 datasets, SVHN and GST. The shared forest method performs better than others in 5 datasets. We can easily observe that no single structure can perform best in all datasets. We also change the sample batch size to study the impact of it on performance of the 4 inference structures. For example, for Hedges dataset, when the batch size is less than 10,000, the shared memory method performs best. Otherwise, the splitting shared forest performs best. So, we can get the insights. No single structure can perform best in all datasets with different batch sizes, datasets, and forests. And the usage of shared memory and the reduction overhead impact performance. So, we need a tool to decide which method is best. Motivated by the insights, we use performance modeling to decide which inference structure should be used for best performance. The table lists model notation we used. It includes attributes of forest and bandwidth and thread number of GPU. Most of parameters are measured offline. A few parameters, such as number of threads, number of thread blocks, are measured online. We use performance modeling to decide which inference structure should be used online. The details of performance modeling are listed below, so you can get more explanation from our paper. The overhead includes running performance modeling for each batch of samples. Performance modeling consists a total of 90 floating points operations, which takes up to 3% of an inference time. We evaluate this work using a high-end server with 3 generations of GPU, including Tesla K80, Tesla P100, and Tesla V100. The input dataset includes 50 datasets from UCI and libsvm, in which 70 of each dataset is used for training and 30% is used for inference. The baseline we used is a high-throughput tree library (FIL) in NVIDIA Rapids Suite, which is the state-of-the-art and open-source library. This figure shows the throughput on all datasets. We show performance using 2 batch sizes, 100,000 representing the use cases with high parallelism, and 100 presenting the use cases with low parallelism. It shows that Tahoe performs much better than FIL. For high parallelism tasks, Tahoe introduces over 3 times speedups on average on 3 generations of GPUs compared to FIL baseline. For the low parallelism task, Tahoe introduces over 1.4 times speedup on average on 3 generations of GPUs. We use NV-proof to quantify the load efficiency of shared memory and global memory when accessing forests. With Tahoe, the global memory read throughput is improved greatly on 3 generations of GPUs. We measure the average coefficient of variation (ACV) of execution time across threads in a thread block in 50 forests. The average coefficient of variation is reduced by 16% on 3 generations of GPUs. In particular, the biggest forests gain the largest benefit from load balancing, because there is a large variance in these forests. Tahoe also removed block-wise reduction for 27 cases from 45 cases. For scalability analysis, we evenly partition each inference dataset into multiple GPUs. Each GPU has 1 partition. Overall, Tahoe scales very well as the system scales increases. For some datasets, such as Hawk, GIST, Fission, the performance improvement is not scalable, as these datasets are really small. For weak scaling, good weak scaling we observed comes from the fact there is almost no communication between GPUs. In conclusion, we reveal 3 common performance problems in decentralized inference. we introduced Tahoe, an inference engine on GPU that concises the common paths of tree traversal and the similarity of tree topologies to address these problems. Tahoe largely outperforms an industry-quality inference engine. I'm done with this talk. Thanks for listening.